Okay, so in this video, we're going to do another example using the Jacobian to evaluate a double integral by making a double substitution. We're going to not only let u equal something, let v equal something else. On the previous video, hopefully you watched that, the reason why we wanted to do a substitution on the previous one was more about what we were integrating. We had something that was not going to be very easy to integrate in rectangular coordinates. Here for this example, I need to integrate this function with respect to x and y, and there really is no issue. I can integrate this function easily with respect to x or with respect to y. The issue on this problem is the region I'm supposed to integrate this function on. These lines, which you'll notice, these are two parallel lines, these are two parallel lines. And if you take a second to sketch them, slide this up a little bit, you'll see that they enclose a quadrilateral shape, like a parallelogram. And the issue is if I want to integrate normally with respect to x and y, I get to use either horizontal or vertical cross sections. In fact, the way the integral was set up, it's telling us to integrate with respect to x first, which would require using horizontal cross sections. And hopefully you can see that when you do horizontal cross sections, you want to think right left function. If I drew some horizontal rectangles in here, and my right left function right here is different than if I move up here. Now my left function switches to this line. And if I move into this region, now my right-hand function changes. So if I was going to try to integrate with respect to x first, I would actually have to do three separate integrals, one in this region, and then one in between here, and then another one there. We know from past experience, we could reverse the order of integration, integrate with respect to y first, and then with respect to x, but that would create the same problem, because then I'd be thinking top minus bottom, which is changing depending on where I am. Now my top function changes to this. So we would have multiple integrals to do there as well. And so a nice thing to think about when sometimes the way these Jacobian problems are set up is you'll have an awkward area like this. But the key thing is noticing that the top and lower bounds are bounded by similar functions, parallel lines in this case, same thing with the right bounds. And knowing that our substitutions usually involve letting u equal something x and something y, same thing for v, let's do this first. If I rewrote this equation by putting x and y on the same side, so if I added 3/2 x over to the other side, so 3/2 x plus y equals 3, and if I multiplied through everybody by 2 to get rid of the denominator, what I'd end up with is 3x plus 2y is equal to 6. Similarly here, if I move that over, I have 3/2 x plus y equals 1, multiply both sides by 2, I end up with 3x plus 2y equals 1. And so what that's suggesting is if I make a substitution here and let u equal 3x plus 2y, I'm going to have nice bounds for u. U is going to be bounded between 6 and 1. So I'm going to this suggests letting u equal 3x plus 2y. Okay, let's see. Similarly, if I take these two parallel lines and move them over, this is the same thing as 1/4 x plus y equals 0. And if I multiply through by 4, I get x plus 4y is equal to 0. Move this over, multiply by 4, x plus 4y is equal to 4. So what would be a good choice for v? Let's let v equal x plus 4y. Now, we have a couple things to do. We do have to compute the Jacobian, but maybe at this point, it would be a good idea to talk about the boundaries here, right? We had 4 boundaries. A typical problem, we have to take all 4 of those boundaries and convert them to UV boundaries. And the way a lot of times, if you want to do it sort of brute force way, if I took one of these boundaries, for example, if I took the upper boundary here, y, and I guess it's the right boundary, y equals -3/2 x plus 3. If you want to do it sort of the brute force way, y equals -3/2 x plus 3, we haven't found equations yet for y in terms of x and v, but you'd plug them in here and you'd get kind of a big mess. But we already know that that line, 3x, that was 3x plus 2y equals 6, corresponds to u equaling 6. And the left line corresponds to u equaling 1. This is v equals 0, v equals 4. So all four of these lines, I guess this one's technically u equals 6. The other line, which was, why don't we just write it the other way, which was 3x plus 2y equals 1, that corresponds to u equals 1. You can skip a bunch of messy work inside here, which sometimes you have to do, but in this case, we don't have to. My other two boundaries were x plus 4y is equal to 0. That's going to correspond to v being 0. And x plus 4y equals 4 is v equals 4. I feel like I messed up on one. Yes. Okay. Maybe you caught this one. I multiplied both sides by 2 on this one. This should have been a 2. Multiplied both sides by 2. So that was really 3x plus 2y equals 2, which changes this to u equals 2. Sorry, down here. 3x plus 2y was supposed to equal 2, so that's really u equals 2. Now, we do have to compute the Jacobian matrix determinant. So we are going to want equations for x and y in terms of u and v, and there's many, many ways to do that. What I usually do is I'll look at these two equations and say, well, which one's easiest to solve for one of the variables? And right here, I'm seeing it would be really easy to solve for x. So if I solve this for x, I get x is equal to v minus 4y. And then what I'm going to do is plug this into my other substitution. So that's going to give me u equals 3x, so 3 times v minus 4y plus 2y, distribute minus 12y plus 2y. I want to solve for y, so why don't we, this is going to be negative 10y. So let's move that over here, subtract the u over. So I'm going to have 10y over here equals, I'm going to write that as negative u plus 3v. So if I divide by 10, I have negative 1/10 u plus 3/10 v. I just wanted the u first. So there's one substitution that I used to solve for y. Now I want to solve for x. Again, you could switch, you could try something else, but since to solve for y, what I did was solve this for x and plug it in. To get an expression for x, I think I'll solve this for y. If I solve that for y, move that over, hopefully you can see y would be equal to v minus x over 4. And then I would plug that in. And let's bring this down here. So then I'm going to get u equals 3x plus 2 times v minus x over 4. We could multiply, I don't really like dealing with fractions, so we can multiply both sides by 4 if we want to. Get rid of that. 4u equals 12x. Here the 4's will cancel, so it'll be just plus 2 times v minus x, so I'll distribute 2v minus 2x. I'm seeing a 10x on the right side, so I'm going to move the v over. 4u minus 2v equals 10x. So x would be, divide by 10, 4/10, which I guess is 2/5 u, minus, divide by that, 2/10, so 1/5 v. Now I have expressions for x and y in terms of u and v. So we're going to compute the Jacobian. But yeah, just to remind you, I mean, this is, if what the other way to do it, it would be a lot of work, but now you have expressions for x and y in terms of u and v. What they typically do is you would plug y in here, x in here, and simplify this whole big mess, but it would end up simplifying to these boundaries we already got. So that makes our life a little bit easier. So yeah, let's graph our UV boundary. These are just constants. This is just going to be a rectangle, or I guess more accurately, a square, because we had U going from 2 to 6, V going from 0 to 4. This is now our region of integration. This is V equals 4, U equals 6, U equals 2, U equals 0. So we have a rectangle now, very easy to integrate through. But as we know, the idea is this original region of integration, we've now transformed into a rectangle, but there could be a magnification or contraction factor that we talked about on the first video. We have to figure out how much the area has increased or decreased by when we have that new transformation, and that's what the Jacobian measures. When we take this determinant, let me rewrite my x and u. So I have x is 2/5 u minus 1/5 v, y negative 1/10 u plus 3/10 v. So my Jacobian, partial of x with respect to u is 2/5. With respect to v, negative 1/5. Partial of y with respect to u, negative 1/10. With respect to v, 3/10. Jacobi, multiply this times this, so that's 6/50 minus negative 1, negative 1, 1/50 is 5/50, or 1/10. There are some situations, I don't think I mentioned this on the previous video, if your Jacobian comes out negative, if you had assigned maybe u to be the other, your u and v were my v and u, you might have gotten negative 1/10. And so we always take the absolute value. We're looking for a positive value for the Jacobian of how much the area expanded or contracted. Okay, so now we're going to do the conversion. And here's another thing to notice, which really confirms that we took the right choice for u and v. If anybody noticed, this function that we were asked to integrate actually factors into 3x and x. This is plus 4y plus 2y. Check that out. That's going to be 12xy plus 2xy is 14xy. And there's my 8y squared, which was exactly, right? This was my choice for u, and this was my choice for v. Really, I got it from the boundaries, but this is an extra added bonus, right? I get to integrate something really easy in terms of u and v. So finishing this off, I'm integrating u times v times the absolute value of the Jacobian. I don't think I did that last time. The absolute value of my Jacobian, which is going to be the absolute value of 1/10. And then you have your choice. It's either dv du or du dv. It doesn't really matter since we have a rectangle. We'll go ahead and do dv du. So u times v times my Jacobian was 1/10. My bounds for v went from 0 to 4. My bounds for u went from 2 to 6. And if you go through and do that integration, you should be able to do that. It's pretty easy. You should be able to show that the final answer for this ends up being 64/5. Okay, so hopefully that helps. Another example with the Jacobian. Let me know if you have questions. Thanks for watching.